In the previous chapter, we looked at the construction of atoms. How are atoms, what are they comprised of, right? And we saw that we have the nucleus, which contains the protons and the neutrons, and make up most of the mass of the atoms. And then we have the electrons, which are found in shells outside the nucleus, and they're used when atoms connect with each other through chemical bonding. All right, now we'll examine chemical bonding in later chapters, but for now, let's focus on what the nucleus itself does. All right, it turns out that in the case of some heavier elements, and even in not as heavy elements, it is possible to have some interesting phenomena happen with the nuclei of atoms. Either they are unstable and they break apart and do interesting things as they break apart, or it is possible to make them unstable and then break apart and do interesting things when they break apart, or even sometimes fuse nuclei together. In this chapter, we're going to look at all of the cool things we can do with the nuclei of atoms. So first, let's talk about radioactivity. Now, we introduced the concept of isotopes in the previous chapter, right? We learned that isotopes are atoms of the same element that have different number of neutrons. So they would have different mass numbers as a result. Okay. Now, it turns out that some of these isotopes wind up being unstable. Okay. Generally, as you have too many nucleons, that's protons and neutrons, and your nucleus starts to get heavier, typically this has a destabilizing effect on the nucleus. All right. So in the case of isotopes that happen to be unstable, we say that they are radioactive. Now, what does that word mean? It means that when the nucleus basically kind of splits apart into more stable nuclei, it often gives off particles that move with really high energy and other forms of radiation, which is just energy and particles that are radiated outwards, they're emitted. Okay. Now, just a refresher from the last chapter, when we refer to isotopes, typically to refer to a particular isotope, you want to say the name of the element and follow up with the mass number. So that way you know that you're talking about that isotope specifically. So for example, over here, we have iodine with its atomic number of 53, which isn't as important because all iodine has the atomic number 53. But what's really interesting here is that mass number of 131. Okay, so that mass number of 131 needs to be referred to specifically if you want people to know that you're talking about this isotope. So we would call that iodine 131. You just say the mass number after the name of the element. Okay, so something to keep in mind in this chapter, because you want people to know which isotope you're talking about, because if you just say the name of the element, that's not really quite clear. Okay, now when it comes to some of the lighter elements, they tend to be pretty stable. That being said, they do have radioactive isotopes. All right, you can see, for example, here, magnesium and iodine have stable isotopes, but you can see that they have some other isotopes that are less common that are going to be radioactive. As you start getting into the heavier elements, okay, you're getting down to the lanthanides and the actinides and some of the heavier transition metals in general, you'll start noticing that they don't have any stable isotopes. All of their isotopes are radioactive. Okay, they just aren't very stable. Okay, once you start getting to like some of the really heavy elements, like towards the end of your periodic table, you're starting to get into elements that are so radioactive that they don't really, none of their isotopes really last very long. They pretty much disintegrate as soon as they're made. So some of those are just more of an academic exercise. You make them in a lab and show like, hey, this element's possible. We've got proof of it, but there isn't anything practical you can do with it because it doesn't stay that element very long. All right. But that being said, for some of these isotopes that are, that do exist in nature, like uranium, even though they are found in nature and they exist in large quantities, they don't immediately disintegrate. the fact is that they do eventually decay. They do eventually disintegrate, giving off radiation. Okay, this, by the way, is why uranium is very useful as a fuel for nuclear power plants. Okay, so we'll talk more about that later in this chapter. But I'm just pointing out that it is possible to get some elements with heavier and therefore only radioactive isotopes. All right, so let's go through a little review from the last chapter just to make sure we pull in the necessary information from that previous chapter that we're going to use here. Let's look at an isotope of thallium-201. All right. Now, ask yourself, how many protons are in thallium-201? How many neutrons are in thallium-201? And then write out its atomic symbol, which, if you remember, you write out the two-letter code for thallium, and in the top left corner you put its mass number, and the bottom left corner you would put its atomic number. Okay, you may need a periodic table for this, okay, to look up thallium. So go ahead and do that. Pause this video if you need, and then come back here and we'll look at the answers. So thallium, which has the symbol TL, is element number 81. So that tells you that it has 81 protons. Now, the mass number, which is given to you in the question, you're told that is thallium-201, that lets you know that it has 201 nucleons. It's got 201 protons and neutrons combined. Well, if 81 of those are protons, that tells you that the remaining 120 must be neutrons. So, how do we write out that symbol? We write TL for thallium, we put the 201 mass number on the top left, and you can put the 81 atomic number on the bottom left, which again is optional. As long as you have that mass number, that's the important thing. Okay, even if you don't write that 81 there, you can figure out the atomic number of thallium by using a periodic table. So I mentioned that when these unstable isotopes start decaying or breaking apart or disintegrating, they give off what we call radiation. Now, radiation comes in different forms. Okay, we're going to spend a few slides talking about these different forms. So we have alpha particles, beta particles, gamma rays, sometimes just regular subatomic particles like protons, neutrons, electrons, and stuff like that. Okay, so something to keep in mind. You'll see that these different types of radiation are themselves very different from each other. So let's talk about each of them in turn. An alpha particle, sometimes represented with the Greek letter alpha, that's a lowercase Greek letter alpha, or using the symbol for a helium nucleus, okay, is pretty much just that. It's 2 protons and 2 neutrons, which are just the nucleus of a helium atom, right? So it's like a helium atom minus the electrons. Now, with that being said, since it has 2 protons and no electrons, it has a +2 charge. Also, because it has 2 protons and 2 neutrons, it has a mass number of 4. It weighs about 4 atomic mass units. Okay, now that's pretty light compared to most elements, but you'll see as we look through some of the other forms of radiation that's comparatively heavy. So you'll find that alpha particles are one of the less dangerous of the types of radiation we're going to look at. Okay, if the name alpha particle rings a bell, you might remember in the last chapter, these are the particles that Ernest Rutherford used when discovering the nucleus in his gold foil experiment. Okay, so they're small particles, but compared to all other forms of radiation, they're relatively big and slow, and therefore less dangerous. A beta particle, represented with the Greek letter beta, or the symbol for an electron, is essentially a high-energy electron that comes about because a neutron is converted into a proton. Now, when this happens, in order to balance out the mass numbers and atomic numbers, which is something we're going to practice in a little bit when we do nuclear equations, in order for this to work out, basically you have to have a beta particle also spit out to help balance things. Okay, so you can kind of see it in the way this equation is written here. We start off with a neutron, which has a mass number of 1 because it's a neutron, and an atomic number of 0 because it's a neutron and not a proton. And when we make a proton, which has a mass number of 1 and an atomic number of 1, a proton is the same thing as a hydrogen nucleus, so that's why sometimes we use the symbol for hydrogen there. Okay, so notice that we have a mass number of 1 and an atomic number of 1 here on the right side of this equation. So in order to balance this out, we need a mass number of 0 and an atomic number of -1 for this to work out. Okay, so 1 plus 0 is equal to 1. 1 and -1 is equal to 0. All right, we'll look at this in more detail when we get to nuclear equations, but just pointing out that's why the mass number and atomic number for our beta particle is what it is. I think the -1 atomic number throws off a lot of people, but the reason for it is because it comes about from your atomic number changing from 0 to +1. Now, it is possible to have what's called a positron. A positron is like a beta particle, but instead of being negatively charged, it is positively charged. So instead of an electron, it's a positron. Hence the name. All right. So just like a beta particle, it has a mass number of 0. The only difference now is that instead of a negative charge, it has a positive charge. Instead of a -1 atomic number, it has a +1 atomic number. All right. And this basically comes about when a when a proton changes into a neutron. Again, to get things to balance out, the mass number has to, the atomic number has to be +1, okay, for things to work out. Next, we have gamma rays. Gamma rays are represented with a Greek letter gamma, a lowercase Greek letter gamma. So, basically, it isn't really a particle at all. You kind of just have, it's a form of electromagnetic radiation. Since it isn't technically a particle or expressed as a particle, typically, we use a mass number of 0 and an atomic number of 0 when representing it. All right. It also doesn't really have a charge. It has a charge of 0. It's neutral. All right. Again, we'll look at how it comes about, but typically it comes about when a nucleus shifts from an unstable higher energy state into a more stable lower energy state. Okay. We like electrons can kind of do this with electron configurations where you have electrons go from a higher orbital to a lower orbital, like we saw in the Bohr model of the atom in the last chapter. It turns out that nuclei can also do this in a certain way. All right, the parts of the nucleus can kind of change their energy states, and in doing so, they emit these gamma rays. Okay. So what I need you to remember from this section we've just gone over is really summarized in this table. Effectively, when we get to nuclear equations in a little bit, you're going to want to remember these particles because you kind of have to represent them in these nuclear equations, or at least recognize them in some cases. So you want to be ready to identify what these particles are. And I think knowing their mass number and atomic number is also going to be very useful when you start balancing these nuclear equations. All right, so I really recommend that you memorize these symbols as well as their mass numbers and atomic numbers. Okay, here's a learning check that just helps you practice this. I'm going to gloss over for now, just because you haven't had time to actually memorize any of these. So when you're going through these slides later on, feel free to pause here and then go to the next slide and check your work. Okay. When it comes to protecting yourself against radiation, you want to take into account the strength of the radiation. You need different levels of protection depending on how dangerous the radiation you're facing is. Okay. For example, I mentioned that alpha particles, as far as radiation goes, is really not so dangerous. Alpha emitters typically don't require a large level of protection. If you're wearing just regular clothing or using some relatively thin shield like paper, that should be sufficient to block alpha particles. Beta particles, which are a little bit higher energy and smaller, might be a little bit more penetrating, and so you need a little bit better protection. You might need thicker clothing, like certain protective equipment like a lab coat or gloves that might protect you from beta particles. when you get to gamma rays, now gamma rays are really dangerous, right? They're really high energy radiation. So you're going to need something really dense like lead to block it. Likewise, really thick concrete also winds up being a thick enough and dense enough barrier to block gamma rays. Okay, that's why you'll probably notice that a lot of radioactive sources are stored in lead-lined boxes. Or if you look at a nuclear power plant, they have like really thick concrete walls. Most nuclear chemistry research facilities also do the same thing. They have lead-lined and concrete-lined walls just to prevent radiation leaking out, in case you make any gamma radiation. This, by the way, is also why when you get an X-ray taken at the dentist or the doctor, they often make you wear a lead apron. That's just to protect the rest of your body from the X-rays they're using to take the X-ray. X-rays aren't as bad as gamma rays, but they're pretty close. They're just one level down from gamma rays. Okay. In addition to using shielding, we can, just simply limit the amount of time we spend in radioactive zones, and we can also just increase our distance. If you can work with a radioactive source at a distance, definitely do that. Okay. The limiting time thing is actually something you guys may have seen, depending on where we've worked, for those of you who are in healthcare. But basically, you might notice people who work in places that have a lot of radiation, whether you're in the radiomedicine section of a hospital or if you're working at a nuclear power plant, you often have to wear these badges that have a piece of film covered with different levels of shielding. And based on where the film starts changing color, it lets you know how much radiation the person wearing that badge has been exposed to. And so, typically you keep track of that, and then, that affects when you might be forced to end your shift, essentially. Okay. So, but yeah, and basically just kind of remember those different levels of sort of danger and the different levels of protection we need for alpha, beta, and gamma radiation. Okay. By the way, these concepts of different types of shielding, of changing the amount of time used and amount of distance, we kind of look at that in this week's lab on nuclear chemistry. So for those of you doing the lab report, that might be something that comes in handy to think about. I will point out that actually these types of shielding, I think in particular, provide the answer to one of the questions you've got to examine for that lab report. So something to keep in mind. Okay, so again, here's a practice problem, just summarizing what we just learned. I will point out here, whenever they give you a form of protection, think about not only the most dangerous radiation that helps protect you from, but keep in mind, it'll protect you against anything weaker than that form of radiation as well. So, for example, this first one, they suggest heavy clothing, and they ask, what type of radiation does that protect you against? Well, it protects you against beta radiation, but it will also protect you against alpha radiation. Okay, so keep that in mind when you're answering this question. Okay, so feel free to pause here and try this out. And if you've hit play now, here are the answers. All right. Now, when it comes to two procedural pieces of knowledge I want you to get out of this chapter, those two things are writing out nuclear equations and being able to do half-life calculations. All right. So a lot of this chapter is declarative, just knowing things, knowing types of radiation, knowing how different forms of protection, just knowing different units of radiation measurement, things like that. But in terms of the procedural stuff, the things that you solve, that you do to solve certain types of problems, being able to write a nuclear equation and being able to do half-life calculations are kind of important. Okay, so let's start off with the first of those. How do we do nuclear equations? A nuclear equation is a way to write out what's happening in a nuclear reaction, right? It's if you've got a radioactive isotope undergoing radioactive decay, where it is spitting out radiation as it breaks apart or disintegrates. You want to write that out in a particular format so people understand what's happening. Okay? The way we do this is we write the radioactive nucleus, okay, that we're starting off with on the left of our equation. All right? It's sometimes called a parent nucleus. Or a parent isotope as well. We then follow it with an arrow showing that it's changing. And on the right of the equation, and I've run out of room here, so I've put it on the next line, we put out the new nucleus that's produced as a result. We call that the daughter nucleus, or, actually, I'm not sure why it's called a daughter nucleus, but that's called a parent nucleus and not a mother nucleus, or vice versa, why they don't just call it a child nucleus. I think it's one of those things they never really thought about when they named it, and the name just stuck. But anyway, in addition to that, you also have some sort of radiated particles. Okay, so you want to keep that in mind, that you have to show the pieces that your parent nucleus is breaking apart into. Okay, now here's the key thing. Okay, this is how you're going to tell that your reaction is, or your equation is correct, and also it's going to help you solve the problem when you have pieces missing that you need to figure out. You need to make sure that the mass number and the atomic number on both sides of the equation total each other. Okay, here's what I mean. Let's look through an example and you'll see what I'm talking about. So, here is the radioactive decay of uranium-238 as it becomes a thorium-234 particle and an alpha particle. Okay, so we could say this is alpha decay, basically. All right, this is an alpha radiation or alpha emission from our uranium-238. Now look at how they've written out this reaction. Okay, you start off with your uranium-238 on the left, okay, and it's by itself. That's the only parent nucleus. On the right, we have the daughter nucleus of thorium-234, and we have this alpha particle. And here we represent it as a helium nucleus with a mass number of 4 and atomic number of 2. This, by the way, is again why it's important to memorize those different particles. Okay, because they may have just told you that uranium undergoes alpha decay and left it at that. So they might not have provided this equation for you. You might have to figure this out. Okay, so memorizing that an alpha particle looks like this is kind of important. Now, see what I mean by the balancing aspect of it. If we take the 234 mass number of thorium and the mass number 4 of our alpha particle, 234 plus 4 is 238. Okay, that's what that adds up to on the right side of our arrow. On the left side of the arrow, we have the mass number of 238 for our uranium, and that's the only thing on the left-hand side of the equation, so that also totals 238. Notice that the mass numbers balance. Now look at the atomic numbers. We have the 90, which is the atomic number of thorium, and the 2, which is the atomic number of our alpha particle. 90 and 2 is 92. Notice that the atomic number for uranium is also 92. Okay, so since our mass numbers and our atomic numbers are balanced on both sides of that equation, on both sides of that arrow, this is a good balanced nuclear equation. Okay, and that's what I mean by making sure your nuclear equations are balanced. Because the way these are often set up is that something will be missing from your equation, and you need to figure out what it is. And by knowing that the numbers have to add up, that helps you figure out the missing particle. And we're going to do a bunch of examples now, so you'll see what I mean. So let's walk through each of the different types of radiation and see how we can balance things out. All right. This is also good practice for helping you remember the mass numbers and atomic numbers of those particles. So I pointed out in alpha decay, you produce an alpha particle. So this is called alpha decay or alpha emission, alpha radiation, etc. So you know that on the right-hand side of your equation, you're going to have an alpha particle, which is a helium nucleus with a mass number of 4 and an atomic number of 2. Okay. So let's look at an example where we work through something like that. We start off with radon-222, and we're asked to write out an equation for its alpha decay. So with just that sentence, we know that we have radon-222 on the left of the equation. Then we have our arrow. And we know we're going to have an alpha particle, which is a helium nucleus with a mass number of 4 and an atomic number of 2. We don't know the daughter nucleus yet, so we're going to put a question mark here. We're going to figure it out. Now, we know that the mass numbers on the right of the equation have to equal the mass number on the left of the equation. So what added to 4 gives us 222? Well, it would be 218, right? 222 minus 4 gives us 218. So we know that the mass number of our daughter nucleus must be 218. Now let's do the same thing for the atomic number. What added to 2 gives us 86? Well, that would be 84, right? 84 plus 2 gives us 86. Now, all that's left is to figure out the identity of the daughter nucleus. Luckily, your atomic number does just that. Look at your periodic table and look up element number 84. You'll see that element number 84 is polonium, symbol PO. Okay, you don't actually need to know the name of it because you just need the 2 letters, 1 or 2 letter symbol representing that element. So its symbol is going to be PO with a mass number of 218 and an atomic number of 84. And we put that in our equation, and now we have our complete balanced nuclear equation. Okay? Again, if you want to double check your work, make sure the numbers add up. 218 plus 4 gives us 222. 84 plus 2 gives us 86. That's how we know this is a good balanced equation. And again, of course, you can double check in your periodic table. Element number 84 is polonium, is PO. All right, so that method is used for all the other kinds of nuclear radiation, though of course keep in mind what particle is being emitted, okay? Because accordingly, the symbol and the mass number and atomic number for that particle might be different. So let's look at beta decay, or beta emission. A beta particle, if you recall, is an electron with a mass number of 0 and an atomic number of -1. And again, it gets that because of the way it's produced, because it's the byproduct of a neutron changing into a proton. So with that in mind, keep that, put that in your equation when you're told that you have a beta decay occurring. So for example, here we have the beta decay of potassium-42. So potassium has the symbol K, all right, and we look it up in our periodic table. It has the atomic number of 19. We know the mass number because the mass number is given to us in the question. We're told that we're dealing with the isotope potassium-42. Please, by the way, don't use the most common mass number in your periodic table. That's the average atomic mass of all isotopes of potassium, right? So you want to use the mass number of this particular isotope, which happens to be 42. Okay, this mass number has to be a whole number. Okay, and you've got to, it is one particular whole number, and it may or may not, actually in this chapter it probably won't be related to the average atomic mass that you see in your periodic table, okay? All right, anyway, with that caveat out of the way, let's set this up the same way we did our previous problem. We know that our potassium-42 over here on the left is going to give us some daughter nucleus plus our beta particle, right? Because we're told that we're undergoing beta decay. So we have our beta particle, okay, which we're going to use the symbol E for electron, and its mass number of 0, atomic number of -1. Just like the previous problem, we can figure out the mass number and atomic number of our mystery particle. Okay, so what added to 0 gives us 42? That's kind of a dumb question, right? Because it's just 42. Okay. Where a lot of students go wrong is with the atomic number, because here we're adding a negative number, and I think that throws a lot of students off. So what added to -1 gives us 19? The answer is actually 20. 20 minus 1 is 19. Now that we know the atomic number is 20, we can use our periodic table to figure out what the symbol for our daughter nucleus is. So looking at your periodic table, hopefully you should see that element number 20 is calcium. So we use the symbol for calcium, Ca, and its mass number of 42 and atomic number of 20. Again, we're using the mass number from the question, not the most common average atomic mass that we see as a decimal in our periodic table. Okay, this number has to be 42, not 40, which is what the average calcium atom tends towards. Okay, and again, if you want to check your work, make sure those numbers add up. 42 plus 0 is 42. 20 plus negative 1, or 20 minus 1, is 19. And therefore, it's a balanced equation. Okay? Again, please note, it is the atomic number, this number on the bottom left, that determines the identity of the element. Why don't you guys try one of these yourselves? So here we have a question asking for the beta decay of xenon 133. Okay, so our parent nucleus is xenon 133. If you want to look up its atomic number, you can use your periodic table for that. Its symbol is Xe. All right. So its mass number, of course, is given in the question. It's 133. Okay, and we're told that we have beta decay going on. Okay, so that means on the right of the arrow, we're going to have a beta particle in addition to our daughter nucleus, which we don't know yet. We've got to try and solve that. Okay, so feel free to pause the video here if you want to try this yourself. If you get stuck and you want to, get a hint as to how to lay out this question, because this question is written in just words, right? How do you get meaningful information from this? This is how I would go about it, right? I'd first want to write out my parent nucleus on the left. So we have the symbol for xenon, which is Xe. And as I mentioned, the mass number is 133, given over here. Okay. And we have an atomic number for Xe that we can get from our periodic table. So pull out your periodic table, look up Xe. It's towards the bottom right of your periodic table. Okay, and you'll see that as an atomic number of 54. Now we know that's going to undergo our beta decay, so it's going to become some mystery particle. That's our daughter nucleus that we haven't figured out yet. And it's going to form a beta particle. Remember, a beta particle is an electron with a mass number of 0 and an atomic number of -1. Okay, so this is a good starting point for how you want to proceed with the problem. Okay, because now all you've got to do is figure out this mass number, this atomic number, and make sure these numbers add up to the numbers on the left. And then you can use the atomic number you discover to figure out the symbol. Okay, so if you had gotten stuck earlier and want to now try it, now that you've got a starting point, go ahead, pause the video. Okay, so here's the answer. We have a mass number of 133, which makes sense because your beta particle doesn't have a mass number, so 133 plus 0 is 133. Okay. With our atomic number, what added to -1 gives us 54? Well, it would be 55. Right? 55 minus 1 is 54. So using your periodic table, look up element 55. And that is cesium. The symbol is Cs. Again, you don't need to know the name here. As long as you have the symbol, that's enough to write out this equation. So we have Cs, and once again, you want to make sure, just double check your work and make sure everything adds up. So 133 and 0 is 133. 55 minus 1 is 54. And this is a good balanced nuclear equation. Now, like beta particles, I pointed out that positrons are very similar. The only difference is that they come about with a proton switching into a neutron, and so that winds up giving us an atomic number of +1 instead of -1. Okay. Oh, there's a little bit of a typo here. That should be actually a plus sign instead of an arrow. So that's, you get a neutron and a positron, so feel free to fix that on your slides. Okay, so 1 plus 0 is 1, 0 plus 1 is 1. Okay, that's why a positron has the mass number and atomic number that it does. So let's see an example of a positron in an actual positron emission. Okay, so here we have manganese 49, and its daughter nucleus after positron emission is chromium 49. So here's our positron. Notice that the numbers still add up. 49 and 0 is 49. 24 plus 1 is 25. Notice that we're adding 1 here because the atomic number is +1, not -1. Okay? So, with that in mind, see if you can try this practice problem out. So here our starting material is rubidium-82. Okay, and use your periodic table to look up its atomic number if you need it, which you probably will. Its symbol is Rb, by the way, so you can find it towards the bottom left of your periodic table. And note that this is a example of positron emission, so make sure you have a positron on the right side of your equation. So that's an electron with a mass number of 0 and atomic number of +1. Okay, so feel free to pause this video, and now we'll go through the answer. So here's the setup, right? We have rubidium, which you figure out has an atomic number of 37. Okay, and then we've got our mystery daughter nucleus plus our positron. So what added to 0 gives us 82? Well, it must be 82. What added to 1 would give us 37? It would be 36. Now you use your periodic table to look up element number 36, which is krypton, symbol Kr, which, again, you just need the symbol. You don't really need to know the name. And yeah, and if you want to double check your work one more time, 82 and 0 is 82. 36 plus 1 is 37. So, and element number 36 is Kr. I pointed out earlier that gamma radiation doesn't have a mass number or atomic number. We just use the lowercase Greek letter gamma, and we put in a mass number of 0 and atomic number of 0, right? Because it's just electromagnetic radiation. Now, how do we show this in a nuclear equation? Well, since your mass number and atomic number isn't really changing, right? You don't have a difference in the radiation we're spitting out. The mass numbers and atomic numbers are going to be the same. And of course, since the atomic numbers are the same, so is the identity of the element, right? So here we have an example of an unstable isotope of technetium, technetium-99, which still remains technetium-99 even though it undergoes gamma decay. So how do we show that it undergoes gamma decay? Well, we want to put a lowercase letter m in the parent nucleus to show that it is unstable. Okay, so next to the mass number, you write a lowercase m, and that tells us that this is an unstable version of this isotope. And as it becomes the more stable version that we just write out very simply as a regular isotope, we also have our gamma radiation listed on the product side, on the right of our nuclear equation. Okay, so when it comes to balancing out gamma radiation nuclear equations, it's pretty straightforward. Okay, so here's just a summary. Again, these are the particles we've kind of seen in that table in the previous section, or a couple sections ago rather, that I kind of asked you to memorize. And you can see that knowing the mass number and atomic number helps you balance out your nuclear equation. Now, in addition to decay equations, it's possible to write out nuclear equations for other radioactive processes that involve elements changing and radioactive particles being emitted, or in some cases even being absorbed. So here we have an example of what's called transmutation. All right, transmutation, or at least that word, originally comes from an old alchemy term. Basically, the idea that you could change one element into another using a magical device called a philosopher's stone. All right, and this, I think I may have talked briefly about this idea back when we were looking at Dalton's atomic theory and pointed out, well, this is pseudoscience, right? The philosopher's stone doesn't exist, and you know, there are references to it obviously in a lot of fantasy literature. For example, Harry Potter and the Philosopher's Stone, which I think here in the US is marketed as Harry Potter and the Sorcerer's Stone. But anyway, my point is that transmutation through a chemical process is impossible. And Dalton kind of showed that. However, here's the cool thing. Transmutation is possible through a nuclear reaction. It is possible to bombard an element with other particles and basically kind of shift it into another element through these nuclear reactions. Okay? So in this example here, we have an atom of boron 10, and we're going to transmute it into an atom of nitrogen 13. Okay? So if you want to change lead into gold, which is kind of what most alchemists wanted to do back in the day, that's probably going to take a lot of energy and probably isn't very, feasible, even though it's more practical. But the point is, we can do this transmutation process. Okay, but how do we show this process? Well, we still follow the same rules of writing out nuclear equations as we did before. So in this case, in order to change our boron 10, we need to first bombard it with an alpha particle. Okay, that means we just fire alpha particles at it and smash them together. This collision yields our nitrogen-13. We also get a neutron as a byproduct there. Okay, so let's write out an equation showing all of these pieces. So on the left-hand side, we have our alpha particle, okay, with helium nucleus with mass number of 4 and atomic number of 2. And we have our boron 10, its mass number of 10, atomic number of 5. These are the two pieces we're reacting together to get this process started. Then we have the arrow showing that this process is occurring, and now we have our products. We have the daughter nucleus of nitrogen-13, okay, and atomic number 7, and we also have a neutron that's produced in the process. And remember, neutrons have the symbol lowercase n with a mass number of 1 and an atomic number of 0. Please note that we still follow those same rules of writing out good nuclear equations. Our mass numbers add up on both sides. Okay, so notice on the left, 10 plus 4 is 14. On the right, 13 plus 1 is also 14. Okay, now let's look at the atomic numbers. 2 and 5 is 7. 7 plus 0 is also 7. So you can see how this equation is balanced on both sides of this arrow. And that's how you want to write out a good nuclear equation, even for processes like transmutation. Again, the way you're going to get asked this on a quiz or exam is you will have one of these equations with something missing. By knowing that the numbers have to add up on both sides of the equation, you can figure out what you are missing. So here's an example of that. Here we have cobalt-59 being bombarded with a neutron. It gives off some daughter nucleus and an alpha particle. What is the mystery particle that we produce in this process? Okay, so if you've done pausing this and tried this out, hopefully you'll realize that in order to balance this out, of course, we must know what the left-hand side of the equation, being complete, adds up to. All right, so 59 and 1 is 60. So we know on the right, something plus 4 also equals 60, which in turns out is 56. 56 and 4 is 60. Now let's look at our atomic numbers. 27 and 0 is what the left-hand side adds up to, which is simply 27. So what added to 2 also gives us 27? Well, it would be 25. 25 plus 2 is 27. So with that in mind, we can then use that atomic number of 25 to figure out what is our mystery particle here. And it turns out that it is manganese. Using your periodic table, you look up element number 25. It has the symbol Mn, okay? And you can plug that into your equation, right? And you can, again, double check your work and make sure everything adds up. 59 plus 1 is 60. 56 plus 4 is 60. 27 plus 0 is 27. 25 plus 2 is 27. So we know we filled this out correctly. And then, of course, you can double check that element number 25 has the symbol Mn. All right, so that brings us then to how we measure radiation. All right, the lab that we do this week, you've probably already noticed if you've gone through the lab report that it entails, well, the first part entails balancing out some nuclear equations like we just went over. And then we look at some of the effects on radiation, changing the different types of sources, using the, changing the distance from the source, adding some shields, adding, increasing or decreasing the amount of time we're spending in front of our radioactive source, stuff like that. However, we have to quantify this somehow, and that's what this section talks about. How do we measure radiation? Well, the device we use in the lab, and in general, whenever you've probably seen this device used, usually on TV shows or movies where there's something radioactive, and you see technicians wandering around with something making a clicking noise. That thing is a Geiger counter. All right, and again, if you want to see a video of this, watch this week's lab video, all right, where I basically use a Geiger counter to carry out the lab, and you can hear that clicking noise I talk about. All right, so the way it works is when these particles hit the probe, they generate an electrical current. Okay, the device basically measures that current. Okay, and it kind of gives you a readout based on that current. The more radioactive your radioactive source, the larger the current you see and the more the needle moves on your dial. Okay, so that is basically, in a nutshell, how a Geiger counter works. All right. The clicking noise is just an added thing to make it a little bit easier to sort of qualitatively figure out how much radiation you're dealing with without having to like look at your readout all the time. Little fun fact: Hans Geiger was a graduate student of Ernest Rutherford. So the same Ernest Rutherford we learned about in the last chapter, who worked with the alpha particles and figured out the nucleus. Geiger was a graduate student of his who did research under him. Less fun fact is that Geiger was actually also a very loyal Nazi, but we can't all be good guys in science, I guess. All right, so the next thing to see is, what do we measure our radiation in? All right, so if you're measuring just straight radiation, you'll probably notice something called counts per minute. So if you look at our video from for our lab, you probably noticed that the readout had a little abbreviation that said CPM on it, which is basically counts per minute. Another word for for measuring the straight number of counts of radiation hitting our Geiger counter is the becquerel. This is the number of disintegrations we see basically in a second. All right, the number of disintegrations we see per second, that's known as a becquerel. We can scale this up into curies. All right, a curie is 3.7 times 10 to the power of 10 disintegrations per second. Okay, you want to sometimes measure things in curies because you can have lots of disintegrations per second if you're dealing with a very radioactive source. So having a unit to scale up generally helps. Okay, if you're curious about the names involved here, Curie refers mostly, guessing specifically to Marie Curie, but possibly also involving her husband Pierre Curie. The Curies both did research for Henri Becquerel. So Becquerel was their graduate advisor, and all three of them did research on radiation. Okay, and you probably specifically have probably heard of Marie Curie as think of not the only person, at least the first person to win a Nobel Prize in two sciences. She won a Nobel Prize in physics and chemistry. All right. Also, she I guess one of the other unfortunate hallmarks of their research, especially since these were in the early days of radiation research, and not a lot of was known about the dangers of radiation and how best to protect yourself from it. Both Henri Becquerel and Marie Curie died of leukemia. I think Pierre Curie probably would have done the same, but he died instead in an accident. I think he was run over by a horse and carriage. But he probably would have also eventually succumbed to leukemia as well due to his radiation research. I believe even now, Marie Curie's lab notebooks are still too hot to spend a lot of time with. If you want to read her original research notebooks, you're only allowed to spend a limited amount of time with them, and then they're put away in lead-lined boxes. Okay. A quick note here, by the way, for all of these units of radiation I'm going to go over, I think it's nice to know what they are. Don't stress too much about memorizing the conversion factors between them or anything. I just wanted you to get familiar with those names just in case you come across them. Okay, I think like in terms of the science literacy you're getting out of this class, whenever you hear of an article, whenever you hear about radiation in, let's say, a newspaper article, they often give you measurements of the radiation so you can understand the scale you're working on. But it is important to be able to distinguish between what these units mean. Okay, and that's kind of why I'm talking about this here. But that being said, don't stress too much about these, like the conversions between these units or anything like that. Okay, so if Curies and Becquerels and counts per minute all determine the just raw amount of radiation that is being given out, how do we look at the way this radiation is absorbed by a material? Okay, specifically in biological cases, by biological tissue, right? So here we're going to look at what we call RADs, or radiation absorbed doses. Okay, so there we're specifically looking not at radiation being emitted, but radiation being absorbed by a biological specimen. Okay, now again, you can scale this up. So a larger unit for rads is the gray. Okay, so 1 gray is 100 rads. Okay, so again, if you see a measurement involving grays or rads, just know that we're looking at radiation absorbed doses there. Now, that being said, sometimes you want to be even more specific. Instead of just looking at biological tissue in general, you want to see how does it affect a specific organism. Okay, how does this radiation being released affect people living in the area? If it's near some farms, how does it affect the livestock? Things like that. Okay, if we're looking at the effect on the microbiology ecology nearby, how does it affect microorganisms like bacteria? Now, different organisms interact with radiation differently, right? So, accordingly, you have to take your rads and multiply by a particular factor to figure out what the radiation equivalent is going to be. Okay, and that's what we're measuring here, REMS, or radiation equivalents, which can also be scaled up into sieverts. Okay, so 1 sievert is 100 REMS. We'll see some examples of this in a little bit when we start looking at damage caused by radiation and how this factors into various organisms. Okay. So I mentioned in our lab video that there's radiation all around us, but I also tell you not to panic because the background radiation we experience is very, very low level and not enough to actually hurt us, generally speaking. Okay, they're just sources of radiation all around us. Some of them relatively far away and relatively weak and low emitting. Okay, but that's why there is some background radiation. All right, so that's something to keep in mind. Now, what are the effects of radiation, right? How do you know that you've gotten too much radiation? Like I mentioned earlier in the section where we talked about protection, that you want to be wary of how much time you spend in radiation or how much radiation you're receiving. Well, what are the signs of radiation sickness? Well, typically, you'll notice, just like acute symptoms of, just nausea and fatigue. You might notice hair falling out, stuff like that. Okay, and if left unchecked, you can get some really serious side effects, right? Another acute symptom you might see are just skin lesions and things like that, just immediate skin damage depending on how strong the dose is that you're receiving. And of course, the long-term effects is that you'll probably get some form of cancer. Usually, there is some cell mutation that occurs due to this radiation. That's one of the effects of radiation. It can cause cell mutation, can cause damage to DNA, and some cells might be made cancerous as a result. Okay. All right. Quick note here about REMS. I mentioned that earlier, and you can actually see how what I was talking about earlier about how radiation affects things differently. Okay, a little note here about how this is measured. LD50, if you're wondering what that means, that stands for lethal dose to 50% of the population. So what does this mean? It means if you had 100 people and you gave them 500 REMS of radiation, half those people would die, half those people would survive. All right, so that's basically the level of radiation you need to give. But if you did the same thing with 100 dogs, you would only need 300 REMS of radiation to kill off half the population and allow half to survive. Okay, so notice how the REMS, the radiation equivalents, change for different organisms. I don't know if you've ever heard the expression that the only thing that might survive a nuclear holocaust are cockroaches and Twinkies. That's kind of just a commentary on the preservatives in food and stuff. But the reason for that expression is that insects in general, due to their biology, just happen to have radiation kind of pass through them without affecting them. So you can see that insects have a really high LD50, right? You'd have to give 100,000 REMS of radiation, right? That's a lot of radiation to try and kill insects using radiation. Okay, so you probably want to use a different method of pest control rather than nuking them. is I guess what I'm getting at. Earlier I had mentioned that there were two procedural skills I wanted you to pick up from this chapter. The first, of course, was writing out nuclear equations, and we've seen that quite a bit in this chapter. And I mentioned back then that the second thing was how to handle half-life calculations. All right. Now, what exactly is a half-life? Basically, as a radioactive isotope decays, there's nothing that governs individual atoms decaying. They can decay at any time. However, one of the interesting phenomena about radioactivity is that the time it takes for a sample of radioactive isotope to decay to half of its population is a set value of time for that isotope. And that time limit is repeated pretty much perfectly for a given isotope. All right, so what do I mean by this? So let's say you have 20 milligrams of iodine 131. Okay, if you wait for a certain amount of time, you'll eventually have that decay down to 10 milligrams. Now, this time is called a half-life, right? Because it goes down from 20 down to 10 milligrams. You wait for that exact same amount of time, wait that again, and your 10 milligrams drops down to 5 milligrams, which is exactly half of what you were at in that previous half-life. All right, and then again, if you wait that same exact amount of time, your 5 milligrams will drop down to 2.5 milligrams. Okay, so even though the decay of individual atoms is random, this half-life value is constant, and it's constant for individual isotopes. So the half-life, the length of one half-life for iodine 131 will not be the same for, let's say, an isotope of uranium or any other radioactive isotope. Okay. Now, if we were to plot this, the sample size that remains after each half-life passes, you would wind up with what's called an exponential decay curve, right? Because with each set interval on your x-axis, you have your y-axis decreasing down to half of its previous value. All right. Oh, so you get this sort of nice smooth curve, but and it approaches the x-axis, but doesn't quite get there. Okay, so it kind of, sort of, just rounds out and then moves almost parallel to that x-axis. Right. Now I mentioned that half-lives are different for different isotopes. Right. So you can get some really long half-lives. So you can see here we're dealing with a scale of thousands and billions of years. Right. So you get isotopes with very long half-lives. And over here we have isotopes with half-lives dealing with hours and days. Okay, so much, much shorter. This can yield different applications of these radioactive isotopes. All right, so these really short half-life radioisotopes are useful for applications where we don't want these things to be emitting radiation for long periods of time. So you'll see that in a lot of medical applications. All right, we'll talk about radiomedicine in a little bit. With the longer isotopes, I think probably the most famous one you've heard of is probably carbon-14. All right, I'm not sure if you're familiar with carbon-14 dating. We'll talk a little bit about it in a second. But basically, that's probably when you hear of the practical applications of radioactive isotopes, and especially doing half-life calculations. That's probably the most famous one. We use these really long-lived isotopes for dating or determining the age of really old artifacts. And carbon-14 is really important in this respect because all living things have carbon in them. So any fossil that came from something that was once living can be determined, can have its age determined by looking at how much carbon-14 is left in it. Okay. That being said, you can use this same principle with other things. So a lot of these other isotopes are used for determining the ages of rocks. So for example, the age of the Earth can be determined by using some really old rocks and looking at the levels of these radioactive isotopes. So I mentioned that a good chunk of this is going to involve calculations. How do we apply this knowledge of how half-life work to relating the amounts of material to the amount of time that's passed? Okay. The key thing is to remember that your population cuts down to half with each half-life. So once you know the number of half-lives, all you've got to do is multiply by half each time. So for example, let's say you've got an isotope and you know that it's undergoing 2 half-lives. All right, and we start off with 40 milligrams. How much is left after those 2 half-lives? Well, after the first half-life, our 40 milligrams drops down to 20, and after the second half-life, our 20 drops down to 10. So we could calculate that by taking 40 times half times half. Okay, each half represents the half-life, the 2 half-lives that have passed. Okay, and so 40 times half is 10. For those of you who like exponents, you can take this and sort of condense it into a little bit more easier to write or shorter to write variant that looks like this. Basically, if you take your initial amount, okay, your initial amount times the number half, or 0.5, raised to the power of the number of half-lives. I'll just call that n. That'll give you the final amount we're looking at. Okay, so in this example, if we take 40 milligrams, that's our initial amount, times half raised to the power of 2, or in this case, half squared, which is a quarter, that'll give us that final amount. 40 times a quarter, or 0.25, is 10 milligrams. Okay, that's how this one worked. In the case of an example like this, where there's only 2 half-lives, if you don't like using exponents, this is probably not as useful. It's probably just easier to times half by the number of half-lives, just because it's easier to count that way. This formula is great for when you have a large number of half-lives. So if something has, I don't know, like 15 half-lives, or 300 half-lives or something like that, multiplying by half and counting out the number of times you're doing that gets less practical. It's easier to make a mistake when you're trying to figure out how many times you write times half. So being able to plug exponents into your calculator is probably a little bit easier. So if you need any help with this, or like knowing how to figure out how to do exponents on your calculator, just let me know. All right, but that's one way to relate, to take your initial amount and figure out your final amount of material once you know your number of half-lives. So let's try some problems using that. Okay, there's basically 2 ways we do these problems. The first one is very similar to how we saw that previous problem set up, where you're given an initial amount, you take your number of half-lives, and you've got to figure out how much is left at the end. All right, so this problem we're about to see is going to be similar to that. Okay, the other type of problem you're going to get is kind of backwards. They give you the initial amount, they tell you how much is left, and you've got to figure out how many half-lives have passed. Okay, now when I say you use the number of half-lives, or you figure out the number of half-lives, they very rarely give you that explicitly. They might instead give you an amount of time, as you'll see in this problem. However, you can figure out the number of half-lives from that amount of time. Okay, or vice versa. You might be asked for an amount of time, but you can figure that out from the number of half-lives. Okay, once you know the length of an individual half-life. So let's look at this problem here. Here they tell us that a radioactive isotope has a half-life of 38.1 years. So this is what I mean about them telling you the length of a half-life, and that comes in handy when you're trying to figure out either amounts of times or numbers of half-lives. Okay, so they tell you the sample contains 38 milligrams of this same isotope, and they ask how many milligrams will remain after 152.4 years. Now, again, the key thing here you need to solving the problem is figuring out how many half-lives have passed. So if one half-life is 38.1 years, and you've had 152.4 years pass, how many half-lives are contained in those 152.4 years? How many times does 38.1 years fit into 152.4? Well, to do that, you just simply divide one by the other. You take 152.4 years, divide by 38.1, and you can figure out how many half-lives have passed. So when you do that, plug that in there, okay, we know that 4 half-lives have passed. So once you know that, then solving the problem becomes very similar to the example we did earlier. You've got an initial amount of 36 milligrams, and you've got to figure out how much is left if you multiply by a half 4 times. Okay, so you could do this the way I pointed out earlier, where you ask yourself for each half-life what's half of the previous amount, and do that 4 times. So for example, 36 drops down to 18 after one half-life, 18 drops down to 9 after a second half-life, 9 drops down to 4.5 after a third half-life, and a 4.5 drops down to 2.25 after that fourth half-life. And so that's your final amount. Alternatively, you could use the exponent method, where we take our initial amount of 36 milligrams, we multiply it by half, raised to the power of n, where n is 4, because that's the number of half-lives we're dealing with, and we figure what that is. So you take half raised to the power of 4, okay, that is 1 over 16, okay, and so 36 divided by 16 is 2.25. Okay, let's try the other kind of problem, that problem where we go backwards. Here, they're giving us the initial and final amount of our radioactive isotope. Now, they're not doing it directly. They're doing it a little indirectly, as we'll see in a second. But we're going to work backwards in terms of figuring out how much time has passed, which, in order to do that, we need to figure out how many half-lives have passed. Okay, this is an example using carbon-14 that I mentioned earlier. Basically, you know, when your fossil was still a living organism, when it died, it had 100% of the carbon-14 it was supposed to have. Okay, carbon-14 is just a naturally occurring isotope in carbon, so all of us carbon-based life forms have the same percentage of carbon-14 in our bodies. Okay, and that's for every living thing. So that includes plants, animals, you know, people, anything, right? Anything biological. So once an organism dies, it stops taking in carbon. It stops ingesting. So if you're a person, or let's say like an animal that's eating plants, and that's how they get in their carbon. Well, when you die, you can't take any more carbon from that. If you're a plant, you stop taking in carbon dioxide from the atmosphere, right? When the plant dies. So the carbon-14 that's present in your body, or if you're looking at whatever organism in that body, starts to decay. It's no longer 100%. Okay, and based on that, we're going to be able to figure out how much time has passed. So in this example, right, is, you know, we've got a fossil, and in this fossil, the carbon-14 has dropped down to 12.5%. Okay, so we're trying to figure out how old it is. Now, we want to figure out how many half-lives have passed, and we know that each half-life for carbon-14 is 5,730 years, so we can then figure out how much time that many half-lives is. Okay, but first let's figure out how many half-lives have passed. So the key thing here is you kind of have to go stepwise. There's no nice exponent formula to solve this. I mean, there is, but it's going to involve a little bit better knowledge of logarithms and things like that, which we probably don't want to get into in this class. So we'll keep it simple, and usually it'll only involve a few half-lives, so something we can follow relatively easily. But basically, start off with your initial amount, and ask yourself how much is left after one half-life. Then do that again. Say how much is left after the next half-life. Keep doing that until you reach the final amount that the question gives you. So in this case, we wind up with 12.5%. Okay, so if we started off with 100%, after one half-life, we drop down to 50%. Now, after the second half-life, that 50% drops down to 25%. After a third half-life, that 25% drops down to 12.5%. And this is where we stop because now we've reached the percentage that the question wants us to. Now, how many half-lives did we go through? 1, 2, 3 half-lives, and that's something that we need to solve the problem. So, if each half-life is 5,730 years, according to the question, 3 times that number is 17,190 years. And that's how old our fossil is in this problem. Okay. Now, in this question, the level of carbon-14 was given to us as a percentage. Please keep in mind, it might not necessarily be that way. They might give you radioactivity levels read from a Geiger counter and say that the radiation started at some number and dropped down to some other number. Okay, but the principle is still the same. You're still going to take your initial amount and ask yourself, okay, after one half-life, how much is left? After another half-life, how much is left? And keep going till you get that final amount. So earlier, I mentioned that we can use radioactive isotopes that have short half-lives in certain medical technology. So let's talk about how that works in general, and then we'll look at some specific types of technology that use radiomedicine. The general principle for a lot of these techniques comes from the fact that radioactive isotopes emit radiation, obviously, but that radiation can then be absorbed, and you can kind of get a picture of where that radiation is. Now, radioactive isotopes are still chemicals. They still have chemical properties. And so they will interact on a chemical level with organisms. So specifically, certain organs absorb certain elements. So if you pick a radioactive isotope of that element, or an element that's very similar to it, perhaps in the same group, that organ will absorb that radioactive isotope, and that radioactive isotope is going to emit radiation. Well, since the emitted radiation can be sort of captured and imaged, we can get a picture of what's going on inside that organ without needing surgery. So, here's an example. Let's say we want to examine a patient's thyroid. Now, the thyroid absorbs iodine. Iodine 131 is a radioactive isotope of iodine. So you give this patient some iodine 131, perhaps in the form of a saline solution that contains sodium iodide, where the sodium iodide is enriched with iodine 131. Yeah, I'm just making that up. They might use a different salt, but or a different way of injecting it, but the principle remains the same, right? You're going to receive that element into the body, and it'll make its way to the thyroid because the thyroid is what captures that iodine. Well, you then place a detector that's relatively close to it, and it picks up any radiation that's being emitted. Well, the radiation it sees, so to speak, is coming from the thyroid. And based on the parts that light up, you can get some information about the thyroid and how it's functioning. Now, I mentioned that you want to use isotopes that have a very short half-life. Okay, that's one of the key requirements here. If you notice all of these examples, they all have relatively short half-lives on the scale of days and hours and minutes. And secondly, you want to pick isotopes that will get absorbed by the organ or tissue that you want to study. Okay, so I gave you the example earlier with iodine and pointed out like that's used for thyroids. To give you another example, let's say you want to study bones, right? Well, bones absorb calcium. Now, if you don't have any appropriate calcium isotopes, you can get something that's similar. So strontium-85, for example, is very similar to calcium. It's in group 2 as well, and it can be used to study bone lesions. All right, so here's a quick learning check. It's kind of a silly one, but which of these isotopes are most likely to be used in nuclear medicine? So think about what the two requirements were for having a good radioactive isotope for radiomedicine. Okay, and one of them is kind of addressed in the lengths of these half-lives. So hopefully you guys all picked those latter two, because the key thing is you want a short half-life, in this case 12 hours or 8 days. You definitely don't want to pick up the radioactive isotope that has the half-life that's on the scale of a billion years. Okay, the idea is you want a short half-life so that whatever is emitting radiation quickly decays into something that is chemically different and therefore gets, uh, sort of just kind of leaves your organ, right? It eventually gets excreted out as something else. So, and then of course it's hopefully no longer giving off radiation. So, with that being said, let's look at some specific types of technology, some specific techniques that use radiation in some form or the other. So the first one we're going to look at are called PET scans or PET scans. In this case, the PET stands for positron emission tomography. All right. Now, we talked about positrons earlier and mentioned that they are kind of the opposite of beta particles. They come about when a proton changes into a neutron. You need a positive particle to help balance that out, right? And so positrons are that particle. Positrons, though, are kind of like an antiparticle to electrons. Okay, if you can think of a beta particle being kind of like just a fast-moving electron, a high-energy electron, positron's kind of its equal and opposite in a way, right? Now the thing with in physics is when a particle and its antiparticle meet together, they do what's called annihilation. They both kind of disappear. They annihilate each other, so to speak, leaving behind only energy. In the case of a positron and an electron, this is a small gamma burst. Okay, now this gamma ray isn't, you're not getting like huge levels of it to the point where it'll cause problems, but you're getting a strong enough emission of gamma radiation that a very sensitive detector can pick it up. Now, what parts of the body have a lot of electrical impulses? Well, basically the brain and central nervous system, right? So PET scans can be used for really imaging things like, well, mostly things like brains and nerves. So here's an example. Here is a patient with, or someone, a volunteer with a healthy brain, and here is a patient with Alzheimer's disease. And you can see, based on the level of positron emission, you can see that different parts of the brain light up. Okay, now because this, we can, because of these differences, we can kind of figure out what parts of the brain are being affected. We can figure out what parts of the brain are working, what parts are sort of, just working differently, and so on. And again, the really nice thing here is this can all be done without surgery. All right. Previously, the only way to study Alzheimer's was on cadavers. You could only study people posthumously. Now you can actually have living patients. You can ask them questions. You can show them pictures, or just like in general, like just activate their senses and see how that causes different parts of the brain to light up. In a similar vein, we have computed tomography or CAT scans. Now, with CAT scans, CT scans, the form of radiation we're using here are X-rays. All right. Now, when you think of a traditional X-ray, what it does is it gives you a shadow of whatever you're trying to study. So typically, you would use it to look at things that are pretty dense, like bones or teeth. Okay, so you look at the shadows of those bones or teeth, and then you can see things like fractures in them where the radiation is able to pass through, right? In this case, we are using X-rays with varying intensities. So you have to remember that even though X-rays are like a set type of radiation, they still exhibit a spectrum. You can get different intensities, different wavelengths, and therefore different energies of X-rays. Okay, so by varying that, you kind of fire them at your at whatever you're studying, and you do it in with using different intensities. You kind of get a layered effect. Okay, now just like with regular x-rays where you're looking for a change in density, by using some of these lower intensity x-rays, you can kind of get a little bit more of a nuanced approach to changes in density, not just a shadow. All right. Now, this is really useful when you want to see something that has a stark contrast in density. Okay. So, for example, here is a picture of a brain, and here's a brain tumor. Right? The tumor has a different density than the surrounding brain tissue, and therefore it shows up. In this case, a computer program helps color in the different densities to make it easier to see, but basically the tumor shows up here as a different color. All right, next we have magnetic resonance imaging, or MRIs. Okay, now MRIs are kind of interesting. This technology in general is kind of neat because it takes it's actually like I talk to this quite a bit with my organic chemistry students, because we have a very useful technique in organic chemistry called nuclear magnetic resonance, NMR, that works on a very similar principle. In both cases, you need a very powerful magnet. The magnet causes your sample to have its atoms, or the nuclei of its atoms, to start spinning in alignment with this magnetic field. Okay. Now, this subject here, in the case of MRI, is a person, right? Whoever you're imaging with the MRI. With an NMR, you're using a just sample of whatever chemical you're studying. Okay. So what happens is these atoms, the nuclei of these atoms, start spinning in line with this field, this magnetic field, and then you fire a radio pulse at this sample, okay, or in the case of MRI, at the subject. This causes this alignment to break briefly. These atoms, these nuclei are still spinning, but they spin out of whack a little bit, and then they gradually relax back down and get realigned with the field. Okay? Well, the change in all these atoms can produce a noticeable effect, and a detector picks up this effect on the magnetic field. Okay. Now, in the case of NMR, this is plotted as a graph, and if you go on to take Chem 204 with me, I would then teach you how to read said graph, and you can actually figure out a lot of really cool information about the chemical structure of what's in your sample. All right. But with MRI, what's really neat is you wind up getting an image of the subject matter you're studying. All right. So basically it winds up looking, you get another way to sort of image or get a picture of whatever your imaging software is focused on based on this data, right? Now, here's the really useful part of this. Okay, and this is the really neat thing compared to a lot of other techniques that we've looked at. Right? All of our other techniques involve relatively harsh forms of radiation to get their jobs done. Okay? The thing with magnetic resonance imaging is the radiation involved here are radio waves. Now, we saw in last chapter that radio waves are towards the lower end of the electromagnetic spectrum. They're the longer wavelengths or lower energy ends of the spectrum. Okay, and other than that, you have a really strong magnetic field, but that's not really harmful. My point here is that you are using something that is not particularly dangerous. Now, the benefit to that is you can then use multiple scans over and over again. In other words, you can make a movie of whatever you're studying. So here we have a picture of we have an MRI of a heart. Well, if you take multiple scans over a brief period of time, you can then get an image of that heart beating. And it's easier to look for anomalies than trying to just use a stethoscope alone. Okay, or on this next slide, here's a picture of two people talking. The person on the left is talking in Chinese, the person on the right is talking in German. And with their MRIs, you can then see the difference in speech patterns. So, but again, like the key thing is that we can take a movie of this to study it. We're not reliant on just still images. All right, so that brings us to our last topic in this chapter, and that is nuclear fission and fusion. All right, how do we take these reactions that we've learned and kind of get them to do larger scale applications? Things where we can get large amounts of energy by involving lots and lots and lots of atoms. Okay, well, there's two different ways to do it. Either by taking large atoms and breaking them apart, that's what fission is, or taking small atoms and fusing them together. So let's look at each of those in turn. So in the case of nuclear fission, you take a large nucleus and you bombard it with a small particle that makes it unstable. Well, this will then undergo radioactive decay and form some smaller daughter nuclei. Now, here's the key thing. This reaction also produces more of those small particles that initiate the reaction. Okay? These small particles then go on and hit other large atoms, and the cycle repeats. Okay? We're going to get into what's called a chain reaction, and I'll show you how that works in a little bit. So here's an example of a nuclear fission reaction. Let's say we start off with an atom of uranium-235, and we bombard it with a neutron. Now, when this uranium-235 absorbs that neutron, its mass number increases and you get uranium-236. Well, uranium-236 is very unstable, so it undergoes radioactive decay. It splits apart and makes smaller nuclei. So, for example, you could have smaller nuclei like krypton-91 or barium-142. There's, a bunch of different other examples. And to be honest with you don't have to memorize what forms, because mostly you'll be just balancing nuclear equations. Okay, and that's something you can do just with your information in the question. Now, if you look at the mass of your daughter nuclei compared to the uranium-236 you started with, you'll notice two differences. Okay, and both involve mass. You'll notice that the mass number and atomic numbers don't quite add up. Or rather, the mass numbers don't. The atomic numbers are probably fine. But you'll notice that the mass numbers don't add up, and therefore we wind up getting some neutrons that go on to bombard more uranium-235 atoms. Okay, that's where that missing mass goes in terms of mass numbers. The other thing you'll notice is that even if you were to account for the mass on both sides of the equation, you'll notice that there is a slight difference in mass. Okay, that your product side, your parent nucleus, is heavier than all of the weight of the products of all the daughter nuclei, of all the neutrons and everything added together. Okay, which from the law of conservation of mass doesn't make sense, right? Where's that energy? Where does that mass go? Well, mass can be equivalent to energy. Basically, that difference in mass can be accounted for by energy that's given off. Okay, now if you want to calculate how much energy, that's where you use Einstein's famous equation, E is equal to mc squared, right? The mass, m, is multiplied by c squared. Now, c is the speed of light. Light travels very fast, 3 times 10 to the power of 8 meters per second. That's a very large number, and we're squaring it, so it's becoming an even bigger number. So a small change in mass can still result in a lot of energy. Okay, and this is where nuclear fission starts getting really useful. Okay, fusion too. That's also going to involve large amounts of energy. We'll get into that in a little bit. But here's an example of that nuclear reaction we just talked about. So we started off with our uranium-235, and we bombarded it with a neutron. Well, when we add that up, we get uranium-236. Okay? Now, that's going to undergo decay, and it will emit we get a krypton-91, a barium-142, and you'll see that you get 3 neutrons here in the process. Now, please note, rather than writing the symbol for neutron 3 times, we just put a 3 in front of it. So this 3 in front of our neutron here is telling us that we're multiplying by that. Okay. In case you're curious, that number is called a coefficient. We're going to see the use of coefficients in equations in our chapter coming up in a few chapters when we start balancing out regular chemical equations. They still work on the same principle of using these coefficients. Okay, but again, all that 3 stands for is that the number of neutrons is multiplied by 3. So anything that follows a coefficient is just being multiplied by that coefficient. Okay, I say this because when you're balancing out your mass numbers and atomic numbers, you want to make sure that you take that coefficient into account. Okay, you want to take this mass and atomic number for our neutron and multiply them by 3 before adding them up. Okay, so 91 plus 142 plus 3 times 1, which is 3, will give us 236. Okay, likewise 36 times 56 times 3 times 0, which is still 0, will give us 92. So with that in mind, we'll do an example. I'll let you practice this. But first I want to explain that concept of a chain reaction. You probably noticed in the previous example, we started off with 1 neutron, and we wound up with 3 neutrons. Well, as I pointed out, those 3 neutrons then go on to hit 3 other atoms. Well, what happens to those 3 other atoms? If each of them produces 3 neutrons, well, that gives you 9 neutrons, which would then go on to hit 9 other atoms. And you see where this is going, right? Now, with each of these collisions and subsequent fission reactions, we're getting large amounts of energy. And this amount of energy increases exponentially. We're going to get more and more energy. Okay? And the fact that these neutrons sort of sustain this continuous bombardment of nearby atoms is what gives us this name, a chain reaction. Okay? This keeps on going on continuously. Okay? Now, in order for a chain reaction to work, to be self-sustaining, you need what's called a critical mass of your material, of your radioactive material. Okay, if you have too small a mass of uranium, a lot of the neutrons that get released can't find another uranium atom to hit, and they get kind of wasted that way. And then there aren't enough fission reactions to sustain your chain reaction. It just kind of fizzles out, right? That's called a subcritical mass. But if you have a critical mass, okay, so once you have enough material together, then this chain reaction happens and it just runs way out of control. Okay. By the way, in case you're wondering how nuclear weapons work, they rely on this concept of starting off with subcritical masses of uranium or whatever material you're using in your bomb, and only when you detonate the bomb do the 2 blocks of uranium come together to make a supercritical mass. Okay, that has a really quick chain reaction. Okay, that, by the way, so that's why nuclear weapons don't just explode in their silos. All right, with that in mind, though, let's have a look at that fission reaction again, and let's try balancing one out. So this is kind of what you would see in one of these types of problems. It's the same balancing of nuclear equations that we saw earlier in this chapter. So go ahead and take a stab at this. You've got a neutron that's reacting with uranium-235, okay, and that's on the left-hand side of your equation. Okay, so maybe add up the mass number and atomic numbers here and see how they work out. And then on the right-hand side, we have tellurium-137, we have some mystery particle, and we have 2 neutrons. Please note the 2 there. Okay, and of course we have a whole bunch of energy, but that's not important right now. We want to balance out these particles. So ask yourself, what must the mass number on this and the atomic number on this be to get this side of the equation to balance out with the left side of the equation? Okay, so feel free to pause this video and try it out. All right, you probably noticed that the mass number on the left, if we add up both halves, adds up to 236. So we need the right to add up to 236 as well. Okay, so we take 137 and 2 times 1, so that adds up to 139, and ask ourselves what adds together with 139 to give us 236, and that answer is 97. So that's why our mass number of our mystery particle is 97. On the left-hand side, we have 92 times 0, so that's 92 for our atomic number, and so we have to have 52 plus 0, or 2 times 0, which is still 0, plus what gives us 92? Well, we need 40. 52 plus 40 plus 0 gives us 92. And so we have an atomic number of 40, which if you use your periodic table, you can figure out that it's zirconium. All right. Common mistakes I see on this type of problem. A lot of students forget that coefficient of 2 when multiplying this. So if you just saw that you have a neutron here and forgot to address that 2 in front of it, you probably got a 98 here instead of 97 for zirconium. So please watch out for that mistake. That's a pretty common one. All right, I mentioned earlier how nuclear bombs work. There are useful applications of fission as well. If you can control that runaway chain reaction, okay, instead of having it be a runaway chain reaction, have it controlled somehow, well, that's a lot of energy that you could harness to do a lot of good. All right. Specifically, since we need a lot of power just to power our electricity grids, having a power plant that uses nuclear fission can essentially give us a lot of energy, give us a lot of power for relatively little cost in terms of fuel. Okay, so if you have so the basic principle of pretty much every power plant is you have some fuel that's heating up water, converting it to steam, and then that steam drives a turbine, which drives a generator, which makes electricity. Okay, so if you want to see a picture of what a nuclear power plant works, how it works, we have our water that gets heated up in steam. The steam gets pushed to this turbine, which drives the blades of the turbine, which runs this generator, and that produces electricity on the grid. The steam condenses back down to liquid water, and it's then just recycled through the system, and this keeps on going. So the only difference between a nuclear power plant and any other type of fired power plant, so whether it's coal-fired, oil-fired, etc., is what fuel you use to heat up your water. And in this case, like I said, we're using nuclear fuel. Now, the key thing there, though, is how do you stop this from turning into a bomb? How do you stop your chain reaction from going out of control, but still being a chain reaction? You still need that chain reaction to produce that large amount of energy you need to heat up your water. But you don't want it running out of control and having a meltdown, right? Okay, obviously that's very dangerous. So to do that, we use what are called control rods. These control rods are made up of materials like graphite or boron or things that absorb neutrons. Okay, so when they are retracted out of the reaction chamber, well, they don't do anything. They're not absorbing it, and your chain reaction goes as normal. Well, if the reaction chamber gets too hot, if there's too much energy because there's too much fission going on, these control rods, which are located on a mechanism that can lower them in, right? So you've got these rods that are on a mechanism that can kind of just lower them into the chamber. They then start absorbing those neutrons. The chain reaction slows down, right? And you start, basically the reactor starts cooling down. Now, of course, you don't want this happening too much because you still want the chain reaction to occur. You still want heat to be produced. So basically, if the chamber starts cooling down too much, the rods get extracted a little bit, and again, the chamber starts warming up. And essentially, that's just a safety mechanism to stop the reactor melting down. Okay, so anytime you hear about a disaster at a nuclear power plant, essentially what's going on is it's either something going wrong with the sensor that tells the control rods what the temperature is, so they stay retracted even though it's starting to get pretty hot in there, or something happens to the actual mechanism where the control rods can't get inserted into the reaction chamber to do their job, or simply you just have a breach of the wall in your reactor, and the radioactive material gets out through the wall. Okay, so for example, like I think at Fukushima, that's kind of what happened. You had your tsunami that an earthquake which kind of damaged the reactor and broke that wall, and radioactive material started coming out. Okay, so that brings us then to nuclear fusion. So if fission is where atoms break apart, large atoms break apart, fusion is where small atoms come together. They get fused into larger atoms. So the most common example of this is where hydrogen gets fused into helium. Okay? Now, keep in mind, this is not easy to do. You're trying to force uh, a nucleus of one atom into the nucleus of another. Okay, there's a lot of repulsion there. It's not easy to do this. You need really high temperatures and pressures to pull this off. So, where do we get these really high temperatures and pressures? Well, if you're at the center of something really massive, the gravity of that massive object will crush that hydrogen into itself. Okay, it will crush multiple hydrogen atoms into each other and build those helium atoms. All right. Now, when you think of things that are really massive, that's where stars come in. Stars are really massive. They have a huge amount of mass. They are large collections of hydrogen and helium gas, and the gravity of this large star causes the hydrogen nuclei to get crushed together and overcome the repulsion between them. And in doing so, you wind up getting energy being released, just like with a fission reaction. Okay, so this process is constantly happening in pretty much every star, right? You have large amounts of hydrogen, and they're constantly being crushed into helium and producing large amounts of energy that we get from those stars, right? We see that as light and other forms of radiation. Okay, so it doesn't stop there, though. Eventually, as you start to run out of hydrogen, your helium starts getting crushed together into and undergoing fusion, and you start building up heavier and heavier elements that way. Okay, I mean, obviously, it doesn't have to wait till you run out of hydrogen. It's just that once you start running out of hydrogen, you start getting more and more of those heavier elements a lot quicker. Okay, so uh, that's basically where a lot of the heavier elements in the universe come from. Essentially, when a star dies and once it's a particular size of star, if it's a really large star, it'll undergo what's called a supernova, where it kind of explodes and gets all these heavier elements and sends them just sends them outwards, where they can get picked up, in as a form of meteorites raining down on various planets and bringing those heavier elements to those planets. Okay. So anyway, I'm going off on a tangent here about how stars work. The bottom line is that's what fusion is, where smaller atoms are fused together to make larger ones. And again, the key thing is noticing that we get a lot of energy out in this process as well. Okay, it's just like fission. The only difference here is your atoms get pushed together instead of breaking apart. Now, I mentioned earlier that one of the really useful uses of nuclear fission is for powering, power plants, right? For getting energy, getting electricity out of them. The downside to nuclear fission is that you're going to wind up getting byproducts. So those daughter nuclei are radioactive, but not the right kind of radioactive to help sustain our chain reaction. So we wind up getting a bunch of nuclear waste that's still radioactive, but not useful. And radiation is dangerous, and so you've got to be very careful about how you dispose of that waste. Got to be very careful to seal it away. Even from a security standpoint, you don't want people like stealing it, because it can make what's, let's say, a very bad conventional weapon and turn it into a much worse nuclear weapon, right? So again, there are a lot of while nuclear power plants are incredibly useful, and they may like help be part of the plan for solving our energy crisis. The problem is there's still like some problems with it, right? It's not like a completely perfect source of power. But what about fusion? Now, obviously, we don't live in a star, right? The sun's our star, but if we lived in the sun, well, we'd die really quickly. Um, so we need to figure out how to do fusion without the large amounts of gravity required to crush hydrogens together. Well, perhaps if we can accelerate the hydrogens fast enough, they'll collide with each other, okay, and then get crushed together that way, just through momentum. Well, this is called cold fusion, and it's one of those holy grails in science that we're not sure if we'll get or not. It's one of those things like where some people are debating, like, well, is it even possible? If it is possible, it's going to be very difficult, no doubt. But if it is possible and we're able to pull it off, that could really solve the energy crisis, because your byproduct here is helium. Well, helium's pretty harmless. And even if you get a radioactive isotope of it, it's relatively easy to contain or get rid of. All right. So my point here is that if we can do cold fusion, that'd be great, right? From just a an energy standpoint. But so that's one sort of earthly example of using fusion. Other than that, we've got to kind of look to the stars for nuclear fusion. So let's end this by looking at just doing a quick learning check. Have a look at each of these statements and ask yourself, do they apply to nuclear fission or nuclear fusion? Okay. Now, one of these happens to be kind of a trick question. So hopefully you're thinking about the answers and are going to write them down. So feel free to pause the video. But here are the answers. Large amounts of energy are released. A lot of people look at that and immediately think fission, but don't forget nuclear fusion also produces a lot of energy, right? That's how stars run. So the answer to B is actually both 1 and 2. Okay, it's both fission and fusion. All right, and that's it for this chapter. So here are some suggested homework problems from the textbook. Feel free to try those. Try any extra practice problems from not those sections. And yeah, let me know if you have any questions.